Should we start? Okay.
Yeah, let's start.
Okay. So we should share the screen here, right?
Yes.
Can they see our video? What's the deal here?
Yeah, they can see you not right now.
All right. Okay, so welcome to the course here on machine learning. So I'm sitting here with my dear friend and enemy, Adam. We might have seen
Ditto.
Yeah, right. So we're gonna be teaching this jointly. We're sitting in the same room right now, which could be very interesting. But normally we'll be teaching from different. Next week I'm going to be out in California, so I'll be teaching it from there, and he'll be from Chicago. So the subject here is machine learning, and we of course uploaded the slides to the platform. So hopefully you've downloaded it. I also uploaded a notebook, and it's on notebook. So if you don't know how to use Python Notebook, the books I would suggest that you learn this. I mean, I think most of you are probably taking VJ's course in Python, so you should hopefully know how to use Python notebooks. If you don't, then you should download the Anaconda Python distribution, which has the Python notebook in as part of that distribution, and that's sort of what we'll be using, at least for my part. Adam will be using R. So if you don't know R, you can submit either in R or in Python. If you don't know Python, you can submit in R. If you don't know R, you can submit in Python. So both languages, I think, are important to know if you're going to be a data scientist. So I'm going to start with something pretty simple.
Just 1 second.
Yeah.
If you don't know how to install R or RStudio, actually, there's an ACADS lecture where I talk about that, an introductory lecture on stats and data manipulation. So that's on YouTube even.
Mm-hmm. YouTube, wow. Mm-hmm.
Okay, I'll share the link, Adam, the YouTube link of that lecture.
It's the introductory one.
Yeah. Okay. Well, we'll get started. So the first slides here are just some introductory remarks about the course and how we're going to be teaching. We're going to be attempting to equip you with some tools. So you can use machine learning when you actually are in a situation where you have a practical problem with data, and you have some data you want to analyze or whatever to use some of those tools in your actual work. And of course, we can only in a 10-week course, which we are going to try to keep on a level that does not use a lot of heavy math. We can't do math, that's for sure. But we hope that we can inspire you to be more, because there's an enormous amount of material in machine learning, and it's a field that's developing incredibly fast. I mean, there are new things coming out almost every single day. So it's really active field. There are a lot of people doing research and a lot of stuff to learn in there. So we can inspire you to go further, either on or in some future courses. So as you can see, we'll be teaching this course, both of us in a sort of a tag team thing. But normally that tag team means that I'm going to be doing the first 45 minutes and Adam's going to do the second. So it's not really that tag team. But we will actually discuss and ask questions of each other. And of course, we also encourage you to ask questions and take part in the discussion. So we'll try to make it as interactive as we can, and it starts with the tools being interactive. And as I pointed out before, we use different tools. I use Python, and Adam is expert in R. So that's a point of various contention, but hopefully we'll try to keep our tempers in check.
Between us, you'll learn Python.
Python. Yeah. Well, we are both. So both of us are mathematicians. We both have PhDs in mathematics, and so for us, it's not machine learning. It's not just learning a lot of formulas and some code. It's to understand what's going on, and a lot of times you find that the things don't work so well. So it's important to try to understand what goes on behind the formulas, so one can see how to fix things if they don't work out. That happens a lot.
And if I tag in for a second, the point is if you just learn the thing as a recipe, like how to use something without any understanding, even if you graduate with the top marks in the world, 2 years from now you're going to be obsolete, because anything that you can learn by a recipe, guess what? This is machine learning. A machine can learn by recipe too, and it'll just be faster than you and cheaper than you. So it's really important, even you don't have to understand the mathematical proofs of things, understand all the complicated algebra and how something comes about, like gradient descent. But if you don't have some idea of what's going on, you'll be mired in one spot. And so I agree with Niels most strongly that we're going to work very hard to try and give you an idea of what's going on, so you'll be able to not just do what we show you, but go beyond it. Right.
And we'll actually show you some examples that actually we discovered while we were preparing the course. We found some things that we hadn't thought about, but it prompted us to really think about these things. So we'll share those things with you. So what we agree on, maybe the only thing we agree on, is that machine learning is prediction. It's about making predictions. It's not about a lot of other things that people have been doing in data science through the years. Machine learning is about how to predict things. It's about making a machine learn enough that it can make some reasonable decision about what's going to happen, different data. So I mentioned that other fields, I'm particularly thinking of econometrics. People in economics and econometrics are more interested in understanding relationships, like causal relationships between various factors and data in the data set, and they're not so interested in predicting what happens. They get some data in, but machine learning is absolutely all about see what happens when you get new data, and try to predict what happens from when you get new data. So this is machine learning is about using computers and training computers on existing data to make predictions when you get new data, and that's something that we hope to really emphasize in the course. It's not econometrics. It's not economics. It's really it's
not
really,
descriptive.
Yeah, not descriptive. It's predictive. So we'll start very simply and look at the model which is known as linear regression, and I think most of you have at least some idea of what this is. And so let's look at some data points here. So I have generated some data points here in the planes. We have a two-dimensional plane here, and we have points here. And the object of linear regression is to try to sort of find a line that best goes through these points. So here are some lines on true points, and we can see that we would probably agree that the yellow line is the one that, in some sense, fits these points the best. The red and the green line, well, I don't know, maybe it doesn't fit so well. But of course, we have to really define what it means for a line to fit these points. Of course, we can't, the way these points are, we can't draw a line that goes through all the points. That's not possible. They're not linear. So let's see how we actually define what means to what the best fitting line, what that means. So in order to do that, we need to do some math here. So a line is given by an equation here of this form here. It's that the coordinate can be expressed as a number a plus b times the x coordinate. So a is called the intercept, and b is called the slope of the line. So the line consists of all points of this form x, y, where x and y has this relationship here. So x here and y here.
I'd like to point out that I agree with him completely on this.
That's surprising.
Can I say?
Wow. Yeah. Well, that's the equation for a line in the plane. So we're trying to find a line, i.e., an equation of this form that fits the data best. So the points that we have in the plane, we're trying to a line that somehow find an A and a B that somehow fits this these points best possible. So let's see what does it mean. Let's define what it means to fit or to go through these points as much as possible. So you see this thing I've drawn here. Here the purple thing is a line, and then I have these data points here spread all over the plane. And so I want to measure how far is the data point here. So this is the one with a red circle around. This is one of my data points. How far is that from lying on the line? Well, my data point has an x-coordinate that's down here and an y-coordinate, which is here. My line, well, also this form a y equal to a plus bx. So if I take the x-coordinate, then there is a corresponding point on the line here whose y-coordinate is given by this. And so I can simply measure what is the distance from the data point here to the point on the line. And I measure it by looking at the difference between the two y-coordinates. Here I had the y-coordinate of the point on the corresponding point on the line. So it's a point that has the same x-coordinate as the data point here. Here's my data point. Here's its x-coordinate. Here is the point on the line corresponding to that x-coordinate. And so I can measure how far away I am from the point on the line by looking at this distance here between the y values. So I can do this for each of these points, these data points, and I can sum up all these differences. That's going to give me a measure of how far these points are from on the line. You see, if I have a point, a data point that is on the line, here I am lucky enough data point that does lie on the line, then this distance is 0. So the error or the difference between the point and the point line is 0. So for all the points, all the data points on the line, this error term is 0. So I could use this to define what it means, to define sort of what the error is between the data point and the line. And do this for every data point. I could compute this. I could then sum them all up. Now, normally you like to take the average, so you take the sum of these and then divide that by the number of data points. So this is one way to measure how far away we are from lying on the line. So you see, the smaller this number is, the better, the closer the data points are to actually lying on the line. So this is one can use this. I take here the absolute value. So that's the absolute value of this difference is actually the distance between the y coordinates. Now it's very convenient, instead of using this measure to take the square of this difference. So if you take the square of this difference, of course, I get something that's always positive, then equal to 0 anyway. And so I can take these squares, one for each data point, and I can sum them up and divide by the number of data points. And that gives me a number. Every time I take a line, draw a line, I can make this, for each data point here, I can compute this difference here and take the average. So every time I have a line as expressed by these two numbers, a and b, the intercept and the slope, I can construct this, or I can construct this number here, which depends on the line. It depends on these two numbers, a and b.
Okay, that's a question?
Sure.
Why do you call it L? Okay. It's a loss function.
Yes, that's right.
So how much you lose by S. I got it.
This is machine learning. This is what we would call the loss function. And so what's the idea here? The idea is that we want to find A and B. We want to find a line. So that means we want to find A and B. We want to find a line A and B that minimizes this number here. So you want to find A and B so that this number here is as small as possible. It can't be 0 because there is no line that goes through all of them. If this number here is 0, well, then because you are summing up positive numbers, a sum of positive numbers can only be 0 if they're all equal to 0. And that would mean that that all the data points lie on the line. And of course, see, that's not possible. So we can't get it to be 0, but we can try to find A and B so it's as small as possible. So that's the object here of this linear regression model here. We'd want to find A and B such that this loss function is minimal. So how do we find a function? Well, we take derivatives, put them equal to 0, and then we try to solve for the minimum. Now this is depending on what kind of function we have. This is not always possible to do that. We can have some highly nonlinear functions that we can't really solve, but there are other methods to do that, to use the approximate method. In this case here, I should say that it is in fact possible to solve these equations here. But let's introduce this method, which is known as gradient descent method. So this is an iterative method that gives us an approximate solution to this problem. We're trying to find A and B that minimizes the loss function L. And so we can find a sequence of numbers that approximates this minimum, this A comma B, arbitrarily well. So how do we do this? We have to take the gradient of this loss function. A gradient, well, that's just a vector consisting of partial derivatives, the partial derivative with respect to A and the partial derivative with respect to E. And so if we take the partial derivative of this function here with respect to A, what does that mean? That means we keep everything but A constant. So yi minus a sum of yi minus A plus bxi, the whole thing squared. We have to take the derivative of that with respect to A, or just a quadratic function in A, because everything else is considered to be constant. And so we hopefully know how to take the derivative of a quadratic function, and this is what we get if we take the derivative of this with respect to A. If we take the partial derivative with respect to B, we get something a little different because we can see here the videos here, but you can see here that B here is not just B alone, but it's B times X. So when we take the derivative of this with respect to B, we get an X out. So we can see that we get the same thing here, except it's multiplied by xi. So that's the gradient. And now the idea is that we're going to start at some point, and we can choose our favorite point. And then we're going to move from this point towards a minimum. And so the way we're going to do it is we're going to take our point here, and then we're going to the gradient and multiply that by a small number, which is called the learning rate. And then we're going to get a new point, A1 comma B1, and we're going to repeat that. So we're going to take the gradient at the new point, subtract that from A1 comma B1, multiplied by the learning rate, subtract it, and then keep doing that. So I'm going to draw something on the board here that sort of explains why this method here is a good method. So I'm going to shift over to the whiteboard here on my wall, and I'm going to try to make a drawing that hopefully explains a little bit about how this works. So I have my function here of the variables A and B, and I can draw. This is a function of two variables A and B.
Hey, Adam, one question. Sorry to interrupt. I think you may have to stop sharing your screen so that the video becomes bigger. Otherwise, right now it's showing up as a small video.
Okay, so we should stop.
Yes. And for everyone on the yes, I still see. Okay, and for everyone on the call, you have an option. If you go to Neil's window, and on the right, you can pin his video. There's an option for pinning his video. You go on his video screen, and on the right, you will see 3 dots. If you click that, you will get an option of pin video. So if you pin his video, you can see that video in a large screen. Let me know if that, you can write in the chat if you are having trouble doing that.
So how can we see? Can you see the whiteboard now? Can you see what I wrote on the board now?
Yes, we can see it.
Yes.
Great. Okay, so the way I'm going to try to illustrate this function here is I'm going to draw what's called a level curve. So I can look at for a given value, I can look at all the points here, such that the function has a given value here. So these are all the points where the function has some value. So on each of on this curve here, the function has the same value. So it's a constant function here. So I can do this for each value C So I can look at these level curves here as C becomes smaller and smaller. So I get something that looks like this. Somewhere in here, I have the point I'm looking for, the minimum point. So how would I get to this minimum point here? So the gradient descent here is that if I start with some point, and there was my A0, comma B0. So that may lie on this level curve here, maybe out here. But the idea is that when I look at this point here, and if I take the gradient at this point is a vector. So that's something that points somewhere. And I put it here, and it turns out that the gradient, the negative gradient, points inwards here. So I can go in this direction here. That will tend to make the function smaller. So if I take a small step here in this direction here, so they say that this is my alpha times the gradient here. I go in the direction, I get to this point here. Now, at this point here, the function has a value. I can draw the level curve, get to this, and then I can do the same thing here. I take the gradient at this point, and I move a little further down, and then maybe I get to a point here, and I do the same again. Take the gradient at this point, so this would be my point here, A1, comma B1. This will be my point A2, comma B2. Here's 3, comma B3, and I keep going like this. And at each step here, I get closer and closer to the minimum. So that's the idea behind gradient descent, that you go from these level curves, you keep going stepwise downwards until you get closer and closer to the minimum value. So if you look at the notebook here, I have here. Wait, I have to share it. I have to share my screen again, I guess. Here we go.
You make it bigger?
Yeah. So I put up the Python notebook as a document that you can download, and you can run this code here. So here's the gradient, the definition of the gradient. So we're just using the formula that we derived here. I have my points xi, comma yi. That's my data points, and I simply compute the gradient for each of these. So minus 2 times yi minus a plus b times xi. That's the first coordinate. The second coordinate is the same thing, but multiplied by xi. And so I can take those into an array, and I can take the mean of these, and that's the gradient. The gradient is this average. And so that gives me a way to, for each point a comma b, to compute the gradient. I start here, this thing here at the point 0, comma 0, and I do this thing I described 1,000 times, and I get this sequence of points. By doing that, you can try to run that yourself once you have downloaded the notebook. So what we get is from this procedure here, we get these values. This is the value for A, and this is A, and this is the value for B that we get after 1,000 steps of this process. You can see here that the B values, they are they're constant here. The A values are still a little bit varying, but it's up to 1, 2, 3, 4, 5, 6, 7, 8, up to 9 decimal points. It's the same. So it's very close to being as precise as we can get. So we take these values as our A and B, and that is the line that fits these points the best. So that's through the definition of what we mean by fitting. We find this line here and drawn it here, and so you can see how well it fits. There you see the sum of the points, in fact, are on this line. So how the process works to linear regression in 2 variables, and it's exactly the same in more than 2 variables. You can't draw it, so that's why we're doing 2 here. So if you're not done with doing economics or econometrics, we will be done now. We will be happy. But we're doing machine learning here, so it's prediction that matters here. So what does prediction mean? Now, that means if somebody gives me a new data point here, I want to predict what is somebody gives me an X value here. So I want to produce a Y value. I want to predict what is the value corresponding to this X value. So, well, how would I do that? I will go up to the line, and I'll look at the point here on the line, and then I'll go and see this is predicted. Prediction of Y value. So the way we evaluate whether this is a good model or not would be how well does it predict when somebody comes and gives us new X values, how well does it predict the actual Y values? So this is what we're interested in. We're not so interested in finding a line that goes through all the data points. We're interested in finding something that we can use to predict new things. So this is a very interesting point about machine learning, and it's one of the really big problems that people have been working on for a very long time. That if we our data points and we make a model, we fit a model to it, like here we fit this line, then it's not for sure that this line is going to do a good job of predicting things. So we might have found a line very, very good at fitting the data we have, but it may not be very good at predicting. So if someone gives us a new data point, it may not give us a very good value. So this is a problem that is prevalent in machine learning, and there's a lot of work trying to figure out how to get rid of this problem, or how to, at least you can't get rid of it, but try to a little less severe. So what we are going to do is, one way to try to estimate how well is a model at predicting. What we can do is we can take the...
Hey Neil, sorry to interrupt. There is a question by Tejas.
Okay.
Tejas, do you want to unmute and ask the question yourself?
Yeah, hi, can you hear me?
Yeah, we hear you.
Yeah, hello, Professor.
Hi.
So in the method that you just showed, like, so there was a multiplier that you used, like, so how do we go about determining that? I think it was 0.01.
Yeah, the learning rate.
Yes.
Yeah, that's sort of the art of the thing. You can play around with different learning rates. Sometimes you will get if you take a large learning rate, so suppose instead of taking 0.1, I took 100. What you would find is in your process does not converge. Let me try to show it to you on the board again. So I should. You see that? Can you see the board?
Yeah.
Okay. So what happens if you take a very large value of alpha here, right? So you start. Let's say you start from here now. So what happens is you take a large value of alpha. That means that you're gonna end up over here.
Oh.
And if you do the same, go from this one and take your large value, you might end up here. And so you can see that you actually have not made your value smaller. So by taking a large value, you may be going back and forth between a small value and a large value. You'll never actually get closer to this point here. So you sort of alternate back and forth. And that's why it's important to not take that learning rate to be too large. So if you get something that doesn't converge, then you should take a smaller one. Okay. So it is kind of it's a little of a trial and error. There are ways to actually take learning rates that are not constant, but get smaller as you get closer and closer to the minimum.
So Professor, would there be a point where after a certain value, it's not going to give us a better, like, I guess, value, like say, after a certain learning rate, like it's 0.1,
yeah.
0.001 is not going to make any difference?
That's exactly the
that can, exactly, right. That can definitely happen. So there are ways to actually make the learning rate. So as you get closer and closer to the minimum, then you would often like to have smaller learning rates. You take small steps there, and so you can make a learning rate that sort of gradually declines as you get closer to the. But in this case here, it's fine because you also, what happens is the gradient itself gets smaller and smaller as you get closer and closer to the minimum. So in some sense, the gradient itself makes it converge, or at least attempt to converge. But it's always if the first thing you would do if something does not converge is make your learning rate smaller.
Smaller.
Yeah.
Thank you.
Mm-hmm. Okay, back to our thing here. So this is actually something you could try to experiment with. You could try to.
Just want to make it bigger?
I want to make it too.
What about just the page?
No, it should be the slide.
Oh, I see. It is a weakness point for me.
Yeah, no, no, that's because it already was. Okay, so one thing you could experiment with to change this number here. So here I've taken a very, let's see, this is not the, see here I've taken the number 0.01. You could try to experiment by putting in a number here and see if it converges or not. And if you put in like 10 or something, you'll probably find it does not converge. So it's a matter. I mean, what we're going to say, if it does converge with a large learning rate, then you would try to do that, because then you get a faster convergence, right? It declines faster if alpha is large. So you take bigger steps if alpha is large, but if you take steps that are too big, well, then you won't converge. So it's a matter of trying different things and see what works. That's sort of the first rule of thumb, that if things don't work, they don't converge, lower your learning rate. So yes, back to prediction and overfitting. So the one solution is to take the data we have and split it into two parts. A set that we use to train our model, so that means fit the line, and then another set that we keep separate from this, and then see how well it performs when we try to predict those values on the test set. So here's a little code that does that. So one of the very useful libraries in Python is scikit-learn, or sklearn. So from this line here, we import the train test split function, and that's a function that simply takes a data set and it splits it into two parts, and you can decide yourself how big a test set you get. Here I want to take a test set that's 20% of the of my data set. So it splits it into two parts, the X train and the X test. So those are the Y coordinates, and then the Y train and the Y test. And so I would use the X train and the Y train to fit my line, and then I would see how well does it predict on the X test and the Y test. Here's the same graph here where I've taken, so this train test split function here has selected from the a test set, also the ones in red here. And I'll only use the green ones now to fit my line. And then I'll try to test it on the red one, see how that works. So the same thing here, except that we now only average over the training points. So we leave out the test points here. And so we do the same thing here for the training set and the A and the B, and we get slightly different numbers here. So these numbers here are slightly different from the ones we got by testing or by training on the whole data set. You can see here the lines are slightly different here. The green line is the new line we get from only training, only fitting to the training data, so the blue data. The lighter green line here is what we get by fitting the line to all the data. So this is a line we get by leaving out the test set. And then we can see how well does it perform on this test set. And we can simply compute the loss function on the test set. And we get what we can call a test error by averaging over these points here, these points in the test set. And we get here a test error of 14.20. So that's a measure of how well this line here, how well this model can be used for prediction. So there are different ways of estimating how well it will perform on a test set, and and one of them is what's called a cross-validation. And cross-validation means that you split the data into a number of equal-sized subsets, and you leave one of these subsets out, line on the remainder, and then see how well it does on the subset you took out. Do this for each one of these, and then you can see which one of these perform the best, and that's what that's a.
I have a question, Neil.
Yeah.
So we saw the test errors. Do we need to compare with the training error to see how good the model did on the test data? We got this 14.20 on test error. Do we need to see what the value was on the training set?
No, we don't actually do that, because we do want to. We're more interested in how well it predicts. There we are. The test error on the error we get on the training set. Mm-hmm. Will be it'll be bigger than what we get by fitting overall the data set. So when we leave out some points, we're not going to get the same fit. But the idea is that you want to keep the test set and the training set completely separate. You don't want to use the test set for anything in terms of training fitting your model. So you don't really want to do anything with the
yeah. So my question is, how do I know like this 14.20 is a good measure or a bad measure? What's the benchmark against which I know that this model
that's why we're doing this cross validation thing here.
Okay.
Because you would try to find the one that performs the best. So you want to do this for a number of test sets. Mm-hmm. And then try to find the one that does the best.
Okay.
And so this is what you do in this cross validation, where you split the data into a number of equal sized subsets. Let's say 5. So then you take one of these 5 out, you train on the remainder, and then you evaluate it on the subset you left out. And you do it for each one of 5 subsets, and then you see which of yours is the best at predicting. So I'm going to wrap up here because all this stuff here is built into Python. You don't have to write your own code for doing gradient descent. You can fit a regression line to a set of points directly in Python. So again, from the scikit-learn library, you have in the sklearn directory linear model, you have a linear regression class that you can use to fit a line. So you simply instantiate this class here. You get a linreg object that you can use to fit your model. And here's the cross-val score. That's a cross-validation score. So what we're doing here is a cross-validation here, and CV means I'm doing 5. I divide my data set into 5 equal-sized pieces. Take one out, fit on the 4 that's left, and then test it on the one I left out. And you can see here, then you get a better, you get negative mean squared error. That's a negative of the number before. But you can see here, one of them gives you a better value than before. Before we had 14.20. Here we get 10. The minus here, don't worry about the minus, the same as it is 10.26. So we have we can also figure out which one of these 5 models that are the best. So this is one way to, from cross-validation, try to find the one that seemingly has the best predictive power. So, yeah, there's just one thing. If you try to do that and try to run the code here and try to code it yourself, you just be aware of one thing in that this function here, it does not like one-dimensional data. So it's basically, it likes what Adam is going to be talking about, very much higher dimensional data, fitting linear things to higher dimensional data rather than just one-dimensional. So it does not like one-dimensional data, and that's why when you have one-dimensional data like we have here, you have to call this shape function -1, 1 that turns it into a vector. So that's what one thing you would have to do. And so by running this code here, where you just all the models in scikit-learn, they call this fit function, and so the fit function, you put in the data, it'll fit your model to the data, and we get the same as we did on our homemade version. That's always good.
Hey Niels, there's one question.
Yeah.
Okay.
Question?
Yes.
Good.
Avinash, you're unmuted, so you can ask question.
Niels, my question was, and this is coming from an entirely non-practitioner, non-mathematical, non-machine learning background, so
Right.
pardon ignorance, but it makes sense to me why you would want to split the data. But what does not make sense to me is that, let us say the data was of a certain quality on both the split sides, right? In which case split doesn't make sense, because you have actually captured all that you needed to learn on one side of the split, and you are basically affirming once again what you've already learned. But if the split was of the quality that it took away a certain sort of a feature set, or whatever you call it, knowledge of that fit, then you would get a large error on the other side, right? When you try to do it. So it's sort of confusing to me. What is the split actually achieving, and what should be try to strive to achieve when splitting, right?
Yeah.
You see the or maybe I didn't put it too well, but I'm sure you saw the confusion behind my question.
I understand. It's a very valid question, because it's what you're trying to do is you're trying to get a measure of how well this model is going to predict on data it hasn't seen before. And of course, what you're having is a small amount of data that you don't let the model see, and then you try to see how well it predicts on this model. That, of course, is not to say that on any new data point it's going to predict how it's going to predict. It's just a idea, getting an idea of how well it does predict. If it predicts really badly on these test set that you kept out of your training data, then it's probably not going to be very good at predicting on new data. But the fact that it does well on a test set is not a guarantee it's going to do well on any test set. So it's only an indication of what how well it would fit. Yeah.
So it's a great question, and I'll talk more about this in a few minutes. But what you're trying to do is you're taking a split and you're hoping that you really randomize it, that both the training set and the test set have all the features. Now, as you say, you could get lucky, and it could be that on the training set you're missing something that the test set has, or vice versa. So how would you do that? Well, this is machine learning. What don't we care about machines wasting their time? So one thing that you do in practice is you repeat this many times with many different training splits. And what you'll see is, maybe one time you got lucky, maybe one time you got unlucky, but if you do it 100 times, you're going to get a strong sense of whether this is the right kind of model. And maybe one time it'll give you a 3.14, maybe it'll give you a 3.12, a 3.4. As long as you're getting things in that ballpark, it's telling you you're on the right path. This model will do reasonably well. So that's what you get about this is you don't just do this once. You do it many times.
Yeah, and it's also like it's a randomized thing, right? You randomly pick out this test set. So by randomizing things, you get you get to avoid things that sort of repeat knowledge you already have into it. So that's why randomizing things gives you a better estimate of how well it's going to on a different set. So randomizing is important in this situation. But it's definitely not a guarantee that it's gonna perform. It's just a one way to measure from the information that you have how well you might hope it will predict and try to select the model. So when you do a cross validation, right, you're getting different models. If you do a cross validation over say 10 splits, as you call them, then you would get 10 different models, and then you could select the model that gives you the best test score. But again, that's not a guarantee that it'll perform well. But it's an indication of what would perform the best.
And imagine you flip a coin twice and you want to know if it's fair or not. It comes up heads once, tails once. Is it a fair coin? Well, hard to say because you only have flipped it 2 times. Now you flip that coin 10 million times and you come up, like 49.3% heads. You're pretty sure. You still could have been unlucky and it really isn't a fair coin. If you'd flipped it another 20 million times, you'd see it, but you have much greater confidence. And that's what's going on here. I mean, machine learning is about statistical measure. It's not about causal guarantees. It's about what's likely. That's the best we can
I think
do.
that's an excellent answer. I think it clarifies to me quite a bit. And I think the heart of it lies, as you said, we don't worry about how many times we run the process on the machine. And therefore, it's almost like necessary and sufficient kind of argument, right? What is necessary and what is sufficient? If it does not work on the smaller set, then we can say for sure that it does not work, right? But if it works here, then we can repeat it many more times on larger data sets.
Exactly. Yeah. Right. That's a good way of looking. Yeah. So I mean, to prevent fitting, it's good to have lots and lots of data and split it in many different ways and train it on have training set and tests and select that in many different ways and see how well they perform on each of them. So it is about having lots of data. That's important. If you have very few data, you're not going to get very good results.
You're unlikely to get very good results.
Yeah, right. Okay, so I will let Adam take over now and go through a sort of a real life, more complicated example, but where you actually can test out to see prediction and training. So there are some homework exercises that we put up here, and some of them may be a little complicated and whatever, but we'll give you a couple of weeks to try out, and of course feel free to ask questions if you have problems with doing these. You might, but feel free to email us and ask questions, and we'll be happy to help you out with that. So there on this thing here, and I will let Adam take over now and do a real live example here. So let's see if we can get his up here.
To show screen.
All right. I'll close this and use. Okay.
Okay, so let's go to the beginning. Oh, no, am I not on it?
What?
Okay, so this is going to have maybe a little less mathematics than yields, but it's based on the same mathematical ideas. So what I want to do is go through an example of some of the things we talked about. And actually, one of the things I really want to talk about is how can we be sure the predictions we get are accurate? So we're going to go and look at something called the Boston data set. And this is a famous data set. And incidentally, the original reason it was collected was something for which it failed miserably and wasn't used. They wanted that housing prices were related to chemical concentrations of some sort, but it wasn't. So the main difference is I'm going to use R, so you'll get a different feel for a different language. And as I said, we're going to use a data set called the Boston Housing Set, and it's information about housing prices. So there's 506 rows, which are 506 houses, with 14 columns information. So there's of information about each house. Actually, the rows correspond to an average for a district. And the most important thing is we want to see if we can use this data set to predict the median value of a house based on other variables. So one difference between R and Python that's important is indexing. Python uses zero indexing, and R uses indexing like mathematics. So as I say in this last thing, if I wanted to index an element that was in the second row in the fourth column, I would say Boston 2-4. Is that going to work? Oops. And not Boston 1-3, as in Python. So that's just something worth noting. And now we got to go back to how do I think it should be? Doesn't like that. Okay, maybe I won't try and do this much. First time running through. Oops.
There. I hope. No.
Okay, we're just going to reload the data. Okay, we're good now. So when you have real world data, the first thing you should always do is take a look at it. Does it make sense? What do the variables mean? So we're going to get the data, this Boston data, from a package called mass, and we're going to use summary, which gives you summary information about all the columns, and head, which shows you the first few rows. So summary Boston, I just said, I told it instead of import blah, 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 you just go library and it gives it to you. So this is import mass as whatever you want it. And then summary Boston gives you the summary information. So there's a variable called crim, zone, indos, which is how industrial it is. And you can see for all these, for every single one of these, it gives you the minimum, the first quartile, the median, the mean, the third, and the max. So it gives you some idea. So, you know, this is the tax rates. And the last one is MEDV, is median value. That's the median value of a home in that zone. And that's what we're going to try and predict. And this slide may be a little small, but you have access to them, you can look. This slide just contains more exact information about what the different variables mean. Now, here's the thing about machine learning. On the one hand, you have to look at the data. You have to be able to make sure there's nothing in there that seems wrong. On the other hand, if you really believe in these ideas, you don't have to be experts in the topic. So I'm just going to skip over that. And as I said, head shows you the first few lines. So this is just something, if you were doing this for real and you'd want to look at this, just sort of get an idea, what does the data look like? And we can see, you know, the 14 variables.
This is absolutely not politically correct, I have to say.
The data?
Yeah.
What's wrong with it? Oh, the percentage. Okay.
The percentage of African Americans. It's okay.
What does it say over here? It says,
BK is the proportion of African Americans by town.
oh, well.
Well,
If it works, it works. So, as I said, we're interested in not just explanation. We're not interested in describing the data, which is what they wanted to do. We're interested in predicting. So if you want to predict, as Neil said, you want to divide the data into two pieces. A training set, which you're going to use to train your model. Now we're going to do a linear regression. And then a test set to see how well does the model work. And it's very important that you don't cherry pick what's the training and test set. The fact that it's a random selection gives you some comfort that what you see in your training set should, work in the test set too. We can, in R, the version of scikit-learn is something called the carrot package, and I will introduce that in following weeks. But for now, we're just going to do this by hand, get our hands a little dirty just to see how these things work. And I'll just use 70% of the data for training and 30% for testing. And that'll be fine, as opposed to the 80-20 that Neil's did. It's really not important. So first thing I did is I set a seed. If you're doing things for reproducibility, you want to do this, get the same answers time and time again. It turns out there's no such thing as a random number. If you set the seed to be something specific, you'll get the same set of random numbers over and over again. So that's important. And then all I want to do is randomly take 70% of, well, roughly 70%. So I'm going to take 350. I'm going to sample from 1 to 506 because I have 506 rows. I'm going to take 350 of them randomly. And the way you index in R is I call the Boston.train. I take the Boston set on the training index, and the test is all the things that aren't in the training index. So Boston.test is just Boston on minus train.index. And the comma is important. That tells me that the fact that it's train index comma means I want the rows, and then I'm going to take all the columns. So by leaving a comma, nothing on the other side, I'm taking all the columns. So all I've done is divided my data set of 506 rows into a test set of 156 and a training set of 350. To do regression in R, just like in Python, is pretty easy. The function is called LM. And if you want specific information on your console, you can type $LM. And R is a language actually that was created for statisticians at Bell Labs to use. So it was made to be pretty easy. So here's the syntax we have. It's Boston.model equals LM, and I want to calculate median value, and that tilde dot. So tilde means it's an equation, and the dot means everything else. So what this means is I take every variable in my data set except the median value, and I want to predict median value. And then finally I tell it that the data I want to use to do this is the Boston training set. So this is kind of the heart of how you do this in R. And in R, everything's an object. So I've created an object called Boston.model that has lots of properties. We'll get to that in a second. But once I run this code, I've created an object, and one of the things it's done is it's done all the gradient descent and everything. It's created a model, and it doesn't care how many coefficients, it's given them all. So I think this is all that. Let's see what it actually did. So as I said, it's an object. And one of the properties this object has is a summary function. So if I hit summary, I just want to push this up a bit. It gives me all the information I want. So it tells me, well, first of all, the residuals, the difference between my predictions and the actual values. The median value was minus 0.5, and it ranged from a minimum of minus 10 to a max of 24. And then it gives me a bunch of statistical information. We'll get more into this in later sessions. One of the things that this suggests is that some of the coefficients aren't useful, are not really relevant. Incidentally, this is more politically correct. It suggests that the black coefficient may be useful, but it isn't that useful. These this column says, according to the standard theory, which we don't believe in, of linear regressions, the probability that the real value of these coefficients of 0 is. So when you see 3.72 to the minus 11, it says it's essentially no chance, no probability that that real coefficient should be 0. So without believing, okay, so there's two things. There's regression and there's least squares. We're really doing least squares. We're producing a model whose coefficients are just linear equations. Ordinary least squares says this is really the right model under a number of hypotheses about the data. And the most important one is that each time all the residual terms are independent and they're random noise. In the real world, they aren't. But that doesn't mean it's not a good model. It just means it doesn't have the properties. So if you had fulfilled all the properties of linear regression, this would say that you had a really good model and that you would predict. But it isn't the way it works. So here I've just written in bullet points, traditional statistics make a lot of assumptions about the model. We're not going to. And in fact, if you check them, they wouldn't hold. And the other thing is the traditional linear model is interested in describing the data set you have. We're not. We're machine learners. We're interested in taking a data set and can we use it to predict. We're really interested in if somebody gave us a new zone in Boston, could we predict the median value of a house there? Okay, so let me give you an example where that might be useful. People buy property tax deeds, right? And so you want it, all a city or state will do is will say, here's, we'll just tell you it's in this zone and that's it. Well, what do you think it's going to be worth? If this model works, you could use this to decide which zones you want to bid in and how much. Okay? So is it? Okay, and I think I've covered the points on here. We really want to see if this model we've produced with Boston with the training data is going to work well with new data. And the first new data we're going to give it is the test data. All right, so we do run into this question of maybe I didn't do so well, but before we go any further, if the model's crappy on the split, it's probably not a good model. So let's see how well it works.
Hey, Adam, I have a question.
Great.
So let's say like of all the independent variables, all the X variables, if few of them are correlated, right? So can you still rely on the significance of the variable at an individual level? Or they can split between the two factors, the loading?
Okay. So Manish is saying, one of the things that can happen is that variables can be highly correlated. Now, in traditional linear regressions, this can be a huge issue. It's an issue we'll deal with. I mean, just because we have 13 variables doesn't mean at the end of the day, we want to make a model with 13 variables. What Niels was hinting at, and what we'll see more in a second, is that less is more. What happens when you produce a model is you give up how accurate it is in describing data to create models that are better at predicting on new data. So if you are just interested in descriptive, in seeing how well to create a model for the 506 zones you had, the answer is no, you leave everything in. And if you're interested in predicting, we'll see next week when we talk about regularization that leaving out highly correlated variables will typically improve predictability. So whether a model will say two highly correlated values have very similar p-values or not is a complicated thing. The problem is it's not robust procedure. And that's one reason why we will use less variables in the end. Does that answer the question?
Yes, thank you.
Okay. So R has a method called predict that makes calculating new values. So here's a quick quiz. first quick quiz. Suppose that the model was perfect, was spot on. For every example that you calculated the prediction, it was exactly the value of the median value of the housing price. And you plotted that, the prediction against the actual. What would that line look like? And here you have a bunch of choices.
It can be, if you want to put some other choice, you can put it on chat.
But let me give you a hint. What this would say is if you were plotting it, that the value of the prediction was the same as the value of the actual value, they'd be the same. So if you predicted 350,000, the actual value was 350,000. If you predicted 198,000, the actual value would be 198,000. Right? So are we ready to close?
Give me a couple, 10 more seconds.
Okay.
We are closing in 10 more seconds. Okay.
Okay, Vox Populi, the popular answer was y equals x. And that's correct. You'd have an absolute, just a straight line across. Maybe I should go to the board and do this?
Yeah.
Okay, so I'll go to the board and illustrate this. Sets it up, I'll erase. So looking at the difference between what you predicted and what it is called a scatter plot. It's produced a scatter plot. Now, what would it mean if this was you always predictions were perfect? Meaning if this was your actual value, you would have predicted the same. Right? So the x value and the y value were here. If you had an actual value out here from your data, the predicted value would be the same. So you would just get the line y equals x. Now, this is a pipe dream. This is never going to happen. But what this means is if I have data like this, your model is doing a pretty good job of predicting. If you have a point, let's say over here, what does this mean? It means your actual y value is small and you're predicting a really large value. It's not a good prediction. So this would be an example of a point where the model didn't work. So the answer is, if your model was perfect, you would just get the line y equals x. Anyone have any questions on that? All right, I'm going to go back. Oops. So here is the actual scatter plot of the predictions versus the actual. So the predictions are just as I drew them on the y-axis. And this actually, to my mind, looks pretty good. You'll notice there are a few points that are way off. Now notice what this corresponds to, houses that are very high priced. It's incidentally a very well-known fact in the housing industry that it's much harder to predict housing prices when the houses are very expensive. But overall, the bulk of the data is like a cloud that kind of looks like a straight 45-degree line. So the model looks like it's not doing so bad. Now remember, this is just on the training data. I mean, excuse me, this is just on one split. Now, and I just want to point out, if you do R, there is this plot function that'll give you 4 plots. But where is it? Having trouble finding the one I want. It does do a QQ plot, which is this one. This is the plot that says, if you look at this, the more that this looks like just a straight line, the better your model is. And this is showing exactly what the scatter plot showed, that it works pretty well, except on the higher price houses, it really doesn't work well. Okay. So one thing we can do is we can, just like Niels did, find out how much on error. So I actually ran code, so I'll explain what this is. But all this is doing the exact same thing Niels did. It's finding the square of the difference between the predicted value and the actual value, summing them up, and taking the average. And so we see that the average is 0.389. Now remember,
you're also taking the square root here. We were taking the squared error. We didn't take the square root.
Okay. So this is what's called the root mean square error, which is a very common thing. So it's saying on average, well, this is kind of the Euclidean distance. So it's saying on average, my prediction was 0.389. So that's $389, right? Because the median value was in thousands of dollars. So it's saying that on average, my prediction was $389 away. That's not so bad. And all I did was I took some...
Except these prices are from 1960 or something.
The prices aren't that high, but we could tell you what they were on average. We have to go way back. But the mean was 22.5.
Yeah, 22,500. Yeah.
So still, the median value was 21,200, and I'm off by about under $400. I think we'd be happy with that in the real world. But you know, the good old days when you could buy a house for $22,000
in Boston.
In Boston. Okay, so here's another quick quiz, and I think I've sort of I've sort of given away B. So is the difference evidence that the model is good? Do you like 0.389? I mean, I've kind of said what I've said, but this is just an opinion. Do you think that's good? And I've kind of said, what does 0.389 mean? But I won't repeat it, so you'll have to at least have paid attention. So the first one is just an opinion. And by the way, you know, if in the real world you make a model, the first thing you do is you look at the results and say, what do I think? Does this look good? Well, I think I gave it away. I mean, but this is what you do, is you look and you see, is this good? Now, is this the end of the modeling process? No, this is just the start. Tell me when you're ready to close, Manish, and I'll stop chatting. We were talking earlier about the fact, what do you do if you got unlucky? Maybe I cherry-picked the data. How do you know I didn't, behind the scenes, you know, cherry-pick things so it'll look good on the test set? Well, in this case, the way you would know that is it's pretty easy. You have code. I mean, I've shown you code. You could go set your seed and see if you got the same results, or at least very similar results up to rounding error.
So, Adam, can you see the results?
Yeah, so the results are pretty conclusive. Everyone agrees that this is evidence that it's a good model. I can't read. Percentage of model variance was the second most popular. Average error, and that is the correct answer. The 0.389 is the average error. Okay. So can we just cross this out? So as I was saying, how do you know I'm making this up? And maybe I cherry-picked the data and found the right test split. And this was the question that was asked earlier. How do you know that when you took this split, it didn't by, or maybe I didn't cherry-pick it, but maybe just by luck, I happened to pick a good split. How do I know that this is? So how would I do that? As I said, did I cherry pick it? Well, you saw it. I took a random split. You can do that yourself. This is reproducible research, as they say. So, and this is a personal point, but one I feel pretty strongly about. When I read a new study shows, and this is a, if you've ever heard of XKCD, this is the reference, jelly beans cause acne, I always say, did they show me the data? And they almost never do, and so I always say, I don't believe it. I have no idea what they did. And it's, you know, there's a lot of evidence that many scientific studies are wrong. But for your own amusement, Google XKCD, do jelly beans cause acne? It's one of the classic cartoons of statistics, if there could be such a thing. Okay, but for number 2, how do I know that this split was good? Here's what we can do. We can go over the entire code again and just pick a different split, right? If I do a different split, I can see if, I mean, I have the code. I can really cut and paste my code. I don't have to do any more work. I can cut and paste the code and do it all over again. You know, the data's already there. I just have to cut and paste the code and see what happens. So here's the code. And there you see I got the same answer because I set the seed at the beginning. So, but we knew that. We knew because I'm just redoing what I did. All this is showing is the exact code I had before, but it's just put in one block. But if you remove set seed, I can put it in a container and just run this over and over again. So this first line is I'm creating a matrix with 500 entries. And I'm calling it error.boot because I want to see what the error is. And now, what's my code? For I equals 1 to 500, so 500 times, I sample from my data set. So what I'm going to do is 500 times, I'm going to create a test and train. So for each I create a training index, which is sample, and divide my data. So I'm creating 500 training sets and 500 testing sets. And for each one of those sets, I now create a model. I see what my predictions are, and I compute that same error. All I've done is I'm indexing by I, in this for I equal 1 to 500, I'm indexing my process 500 times. And incidentally, this won't take any time to run. And then I see what the error is, and I put it in the ith spot in the matrix. So after I've run this code, I will have a matrix with 500 numbers representing 500 distinct errors. For 500 times, I created a test set and saw how well, I created a model with the training set and saw how well it did. Now, what's this going to tell me? Assuming the answers are pretty good, it's going to say that this model really works. It's going to really work in the real world for predicting median values of houses in 1960 in Boston, but you know, that's not the idea. So summary is just a function it tells me. So what do I see? I see the median, the average error I get is 0.387, which is awfully close to the 0.389. And what's the range? They range, well, I have a pretty big outlier of 0.53, but that's still $530. I did this model 500 times, and the worst error I got was $530. The best error was $300. And this is, so what this means, and this was on data it hadn't seen. This to me now is going back to the question that was asked of Niels. This is really pretty conclusive error that this is a good model. If you want to predict the median value of houses in 1960 in Boston by zone, this model will work. Okay? It wasn't just random luck that based on the test train split that it worked. It just works. Now, again, in a future lecture, we're going to discuss this in greater detail, but this is called bootstrapping, in essence. This is a form of bootstrapping. And the idea of bootstrapping is that you have data, you can continually reuse it, and you can get more information out of it than just using it once. But here we go. This is what you do in the real world, by the way. If you want to produce a model, you're not necessarily so concerned of should the coefficient of the third value be 0.42 or should it be 0.40? You're really concerned, should that be a coefficient at all? Is this model a reasonable kind of model? Anyway, for this case, I claim I've given you pretty good evidence that the linear model will work pretty well. Okay, so another quiz. what does that tell us? Was the original error of 395 good? And the second question, if one was interested in predicting, I can't see, I have to move this, and needed to be accurate within $500, would you trust this model? So if somebody said to you, all right, I have another 500 zones, I want you to produce a model with them, would you feel, and they said, I need this model to be within $500, would you think that was good? Would you think you were likely to do that? Okay. So we have 100% so far of yes was the original error of 0.395 good, and 100% of yes that if one was interested in predicting median value needed to be accurate in $500, is this a good model? Why? Well, we saw, we tried it 500 times, and the worst error we got was $500. Does that prove that if we do it the 501st time, the error won't be $600? No. But it does provide some damn good evidence. And that's all a model can do, because we're talking statistics here. We're making predictions. We're not creating causal models. Okay? So just to chat for a second, the first evidence that cigarette smoking causes cancer came from a study, I think in the 1930s in Britain. And they did a simple chi-square test, which examines whether it was likely that the rate of cancer patients in people who smoked was the same as the rate of cancer patients who didn't smoke. And it produced a model which said no. It did not prove cigarette smoking caused cancer. It suggested it. And it allowed doctors to then go on and find out that in fact it did. So, you know, you have to be careful what you're doing. We're not proving that this model has under $500 error, but we're saying it's awfully likely. And it's, you know, it's an old quote that I think actually is originally from Ecclesiastes, but I heard it from Dashiell Hammett. And he said, the race doesn't always go to the swiftest nor the fight to the strongest, but that's the way to bet it. That's where we're at.
So Professor, I have a question. So then is cross-validation and bootstrapping the same thing, or they are different?
No, they're different. Cross-validation is you divide your data set into a number of pieces and use all the pieces but one to train a model and see how it works on the last piece. So if you do five-fold cross-validation, you're dividing this data into 5 pieces. So this one on bootstrapping is sort of like it, but it's a little more sophisticated. And when we talk about bootstrapping, I don't know, week 2 or 3, maybe I think week 3 more, it's a much more robust procedure than cross-validation. A lot of times cross-validation is used when you don't have enough data. A lot of times cross-validation is used in sort of an intermediate step when you need to reuse the data and you can't use the test set.
Yeah. So this is like using the train test split many times over. So at each time you do the train test split, it selects a new random test set.
So in general, if you have enough data, you divide your data into a training set and a test set. Cross-validation is more useful in situations where you don't have enough data. Now, I could have used cross-validation inside each loop to find a better model, but you know that's a bit of overkill. But in general, if you have enough data to do train and test, you don't worry about cross-validation. But you know, when you're building big, complicated models, where you have to, you know, somewhere along the line see does it look good, then you would see if it's looking good, then you would use cross-validation to get an idea of how well the model's estimating.
Thank you.
So a few more points. I call this bootstrapping, and it is, but usually with bootstrapping, the issue is you want to figure out, as I say, you bootstrap with a replacement. In this case, I didn't. There was enough data, and the point I was trying to make was a little different. But bootstrapping, when you use it as a technique, you're usually trying to say, to make more complicated estimates in which you need to reuse the data and over again. When you use it this way, it's a fantastically useful thing. So when, I have so little value, I put personally so little value in it, I won't even bother to go back to the page. But in the page where they had the linear model, it gave you all sorts of estimates. It not only gave you values for the coefficients, it gave you estimates for how likely they were to be, actually zero. It also gave you confidence intervals. I think one of the real weaknesses of the standard model is those confidence intervals are just way wrong. And with bootstrapping, you will see you can use it to produce really much better confidence intervals. So in other words, I tell you, so when we did the test once, I said the average error was $350, say. You could say to me, well, do you really believe that? Is that really logical? Is it reasonable? How accurate does that be? If I give you new data, is it going to be around 350, or is there some chance it's going to be $800 on average? And the answer to that had to be, I don't know. But after we did the bootstrapping, then I could say, yeah, I'm pretty confident. Chances are, if you do this, you're not going to have an average error of over $500 per house. Okay? So bootstrapping will allow you to get not only coefficients that are pretty accurate, but allow you to get confidence intervals. And that's a really thing, because you can then just say, I predict it's going to be this, but you can say, I predict it'll be this, and I feel confident enough on this, I'll bet $1,000 on this. Or I predict it's going to be this, but if you want me to bet more than $5, no thank you. So it's a very important technique.
Okay. Adam, I've got a question. So Neil's got the Jupyter notebook up there where people can practice. Is there something or some assignment or some section of the code which people who are interested in writing in R should be practicing? If you can.
What I can do is I just uploaded the HTML document. I can upload, there's the equivalent of an IPYNB file is what's called a .rmd file. Mm-hmm. And I can upload the .rmd, which anyone who has has R Studio can open, and they can play with the code. The code is there. It's as code. They can run it. They can change it. They do whatever they want. So I'm sorry. I should have given you that one too. I just forgot.
Okay, that's great. So what I'm going to do is I'm going to send the link or upload the link of your tutorial or the lecture where you talked about installing RStudio, so people have understanding of how to install RStudio, and then you can upload the RMD file, which they can.
I will do that. Though, I mean, between you, me, the wall, and everyone else who's in this room, installing R and RStudio is, at least on Windows machines and in the cases of Mac I've seen, is a very, very straightforward project. You Google R. Install, it takes you to CRAN. You install R on your machine, it's 2 or 3, clicking of yes. And then you Google install RStudio, it takes you to the RStudio website. You pick your operating system. It's pretty straightforward. But so for that, it's fine. But I believe also in that talk or the next talk, I talk a little bit about basic usages, how you can use RStudio and some basic functions. So if this R stuff appeals to you, but you're not quite that familiar with it, there's some information about basic R coding.
Okay, and other questions, is there any textbook people should be following?
No.
For better or worse, this is all out of our heads.
Okay, sure. Okay, so probably we can ask, like, if anyone has any questions, they can ask right now, or later they can put it on discussion board, or they can email. But feel free to ask questions. We can have 5 minutes for questions for this session. Tejas, Avinash, Vijay, a lot of people. I don't know many of them, so you can introduce yourself and ask question. Anyone?
When is the homework due by next week? The one that Professor Neil?
We'll give you 2 weeks.
2 weeks.
Okay. Good. Okay. And that's also posted on the website. Yeah, I haven't seen it.
It's in my notes on the last.
Okay.
Which is on the website, I believe.
Yeah, that's on the those.
I just have one comment about like testing and training sets. Probably the way we do the random split, probably, I mean, Adam and Niels, you can comment on this because you do it all the time. It may not be the best way to do it for the financial time series because there's learning on the data. So the later data, which is later in the time series, has some knowledge of what's happening before, what happened in the past. So if we randomly just split test and train, there may be some bias.
That's a good point. That's a good point. You don't want to do this for time series data.
Yeah.
You don't want to do it like that for time.
Not that simple. You have to make sure that you split in time too. That you train on time only on information that isn't available, later on.
Right.
So you train on 1996 and you test on 1997. You train on 2017, you test on 2018.
Right.
So but that's special to, but it's a funny thing because that has to do in a funny way. You are randomly selecting the data, but just the structure of the data is different because you have this time component, which is different. There's an ordering to the data. If you think about it, all, the Neil's example, my example, if you rearrange the order of the data, it meant nothing. I mean, if you change the order of the rows, it changes nothing. Whereas for time series, it really does.
Yeah, it's a.
We can remember the past, not the
right.
future.
I mean, this is not really for time series data in the sense that you can't regress over time. So it's you need different models for time series. So there you need like auto-regression models and stuff like that. But you do need different models for time series. So you will not use linear regression for time series data.
Not
Any
in a
other?
good way.
Yeah. Any other question? Otherwise, we'll end the meeting. Okay. Thank you, Niels. Thank you, Adam, for this very wonderful class. Vijay, you have any comment? You have any questions? Vijay always has some question.
No, I think I thought it was great. Just a quick question first, Niels and Adam, are you planning to talk about time series or we're just doing multidimensional data and different models for that?
No, I don't think we're planning on doing time series data in this. I mean, the model the machine learning models you use for time series are probably a little beyond this course here. But maybe in a later course, but I don't think it's really I don't think we're going to do it here.
Yes, I agree with you. It tends to be very specialized to talk about time series, and
Right.
there's plenty to cover with these multidimensional data sets anyway. So just quick question here. Now, I mean, by the end of this lecture, we have covered multidimensional linear regression.
Uh-huh.
Are we going to, in the next session, are we going to talk more about generalized linear models and just stay in the space of linear regression, or are we moving to other types of models?
Next lecture, we're planning on doing logistic regression and classification.
Which is a generalized linear model.
That is a generalized linear model, but
Yes.
very special generalized linear model.
Yes.
So we're going to classification. I mean, I think most of the course will be about classification.
Okay.
Wonderful. Wonderful.
And after we do that, we're going to spend some time talking about producing models, how you produce the variables you want. As Manish was saying, if you have highly correlated variables, this can lead to issues with producing models. And we're going to discuss we're going to not only continue discussing, how you sort of make sure you believe your model is a good model, but we're also going to discuss how you add into the mix variable selection. Maybe you only want to use 5 models of the 13 in this, and you may end up with better predictions if you take the right 5 variables. And we'll talk about how that comes about and why.
So we'll spend some time on quote unquote feature selection or variable selection.
Absolutely. No. So,
Just one more quick question. I mean, maybe this is mildly technical, but typically when you approach linear regression, one of the measurements of how good the model is the use of R-squared. And I noticed you specifically didn't invoke R-squared in this conversation. We constructed our own error measure, square root error measure.
I mean, R squared is a measure of how well it fits on the training set, right? So that's not what we're so interested in.
And in fact, I'll make an even stronger statement. R squared, you can always get R squared as good as you want by adding more variables.
Yes.
You can add noise. You can add things that have absolutely nothing to do with the behavior you're trying to model. And R squared can't go down. It always goes up. However, when you add more variables, what happens is that while R squared goes up, the predictive power of the model goes down. So R squared is a very poor measure of predictive abilities of models. And in fact, in almost any situation, we'll see when we get into this, when we talk about regularized regression and feature selection, we'll see that the ordinary least square model almost never is going to be the best at predicting. So it's, for our class, R squared is not a particularly interesting number.
So the mean square error or the root mean square error is what we should.
Well, on the test set, on the test set, it's important. So I mean, there are 2 things that you, when you do a machine learning model, you have what's called the bias, and you're going to have the variance. The bias is how well it fits the training data, and the variance is how well it predicts or how well it fits on the test set. And those 2 things are they're not mutually exclusive, but you try to find something that is reasonably well on both the bias and the. But you can't. You are mostly interested in the variance. I mean, you have a model that fits terribly on the training set, but predicts very well. That would be a very rare situation, I think. That's what you would be interested in.
The famous bias-variance tradeoff, right?
What's that?
Bias-variance tradeoff. And I'll give it. This is something where we have a respectful disagreement. No fisticuffs yet. I'll give a different view on bias-variance, and how you interpret them. But you might have, when I computed those error terms, the RMS, the root mean square errors, I only did it with the test set. Had I done it for the training set, as Neil said, inevitably it would have been lower, but I didn't do it because in some sense, who cares? We're interested in predicting. And, we wanted to see how well it predict. And incidentally, the fact that I did it 500 times and every time it predicted pretty well is evidence that this is a good model for prediction. Now, as we said, I could have added, the price of tea in China as a variable, and it would have improved R squared. It would have thrown the, predictions way out of whack. And one of the popular terms for this is that, it's called literally modeling the noise. You can't have the model that fits the data that you create the model too well, because you don't want it to follow every nook and cranny of, data, the idiosyncratic behavior.
Yeah, I mean, you can find a very high degree polynomial that will go through
every data point.
What's that?
A high degree polynomial that will go through every data point.
Yeah, right. But that would be horrible at predicting, right? So you would have a 0 bias, but terrible variance.
Yes.
And as I said, with random noise, you probably can't get 100%, but you get like 90 R squared 99.9. You know, you can get great R squared by just adding noise variables, but then the predictions are gonna.
Yes, and I asked that question to highlight the care you have taken to delineate R squared versus mean square error or root mean square error. Yeah.
I'm sorry if I gave R squared short shrift and poo-pooing.
No, I think it's good. I think it's very important for those who are new to trying to figure out what is the right measure for goodness of a model.
Yeah.
Many discussions that suggest something to do with R squared is helpful and creates confusion. So this is probably very important.
Yeah, well, I mean, again, it depends on what you want to use the model for. You want to use the model to sort of study causality, how much does a given factor affect the output. Then, of course, R squared is somewhat useful in the sense that you want a model that fits your data as well as possible in order to, you want to estimate how much does a certain factor, how much does it affect the output, how important is it, right? But for I mean that for prediction or for machine learners, it's not important because we only care about what it does when they see something new.
Yes.
What it does there.
Well, I would point out if somebody produced a model, an econometric model on a data set and said, you see, this proves it, and they gave it new data and it didn't work, I would say, you see, this disproves it.
Right. There's a question someone is asking, what are the, can you please let me know what are the prereqs to understand these sessions very well? And also, are there any online MOOCs for understanding the prereqs? I think I would say like some basic statistics, matrix, linear algebra, and calculus. What do you think, Adam, Niels?
Yeah, agreed. And for basic statistics, we do have the acads.org class for that. That is online.
Yeah.
Linear algebra, I'm sure there are very good online, resources. I'm just not familiar with them.
Right.
Yeah, I mean that's it's going to be very difficult if you don't have at least a little bit of if you need to know what a matrix is, you need to know what
how to take an inverse of a matrix, of multiply matrix. You need
to know what it means. I mean, you don't need to know how to do it because a computer can do it for you, but you need to know what it means. You need to know what it means to multiply two matrices together. You need to know what it means to take partial derivatives of a function.
Yeah. Okay.
In some sense, Neil's lecture, showed all this because he was taking vectors, so there was linear algebra, and he was taking vectors of partial derivatives, so there's your calculus.
Right.
Yeah, I think that is a prereq for him.
Yeah.
We'll try to keep the mass down, but there's going to be some.
Yeah, no, I think this was right level because we just don't want to dilute the course and make it like any other course. We just want this for serious learners where they get like a right balance of mathematics, the foundation as well as the examples how to use it. I guess that's the idea when we came up with this course.
Yeah, I think so too. I mean, I think it is. I mean, it's not. I mean, if you're just going to use a canned function to do everything without knowing what goes into it or what really is, then it's not really a good thing to use it in practice, because if you don't know what goes on and what you're doing, then you are very likely to make some serious mistakes.
Right.
So.
Yeah, I've seen some examples where people create like a Sharpe ratio of 15. And then out of sample, it's like 0.2 or negative.
Yeah, right. Except when it comes to real money, it's not 15.
All right.
Just one, Adam. What was the quote that you had mentioned about? That's the way I'll bet it.
You always. It's not always the swift who wins and the strongest who wins. What was that, Adam? But you bet on those.
So I read this in a novel by Dashiell Hammett, but looking it up once it came up, you can find it somewhere in one of his novels. But the essential quote is from Ecclesiastes, and it says the fight doesn't go to the strongest, the fight doesn't always go to the strongest, nor the race to the swiftest, but that's the way to bet it.
Wonderful. Thank you.
All right. Thank you, everyone. We'll end the lecture here.
All right.
Thank you, Niels. Thank
Thank
you.
you.
It was great.
Thanks a lot. Thank you.
Next week, and feel free to send emails if you have questions.
Absolutely.
We'll do our best, but we can't for you.
Yeah.
Okay.
Thank you very much.
All right. Thanks.
Good night, everyone.
Bye bye. Good morning.
Good morning.